formula sheet. So you're going to be getting your first couple of new equations. How do we calculate circular acceleration? To be perfectly frank, as much, Jordan, as I love to give you algebraic proofs, this one's a little long and ugly and cumbersome. So I'm going to do something I normally don't do. I'm just going to give it to you. To find the acceleration if you're moving in a circle, well, the symbol we're going to use, the symbol, oh, look at that. My pen's not working. Good gosh, Dueck. Pause the video. If you're moving in a circle, A for acceleration, what I usually do is I add a subscripted C for centripetal or circular acceleration. And it's calculated by V squared over R, where V is your circular speed. It's the speed that you're traveling tangent to the radius. It's V squared over R. And so we have this situation where for an object that is in uniform circular motion, constant speed, changing direction but constant speed, we can say that for an object making one complete loop around the circle, its speed will equal the constant ratio of distance over time. Say what? Don't write this down. True? Since physics 11, actually since physics 10, I've just told you we're at a constant speed. True? Get the V by itself. Get the V by itself. Okay. I said this is the circular speed. Well, Darian, how do you calculate circular or centripetal speed? It starts out by saying this. You can write this down. This is not on your formula sheet, but I just showed you how to derive it, but we're going to go one step further. Jake, in a circle, we have a special name for the distance once around. We call it the circumference over the. And we have a special word for the amount of time it takes to complete something once. We call it the period. The period. Your circular speed is the circumference divided by the period. That's how I derive it. Let me actually give you the equation. It's going to be, hey, what is the circumference of a circle? How do I calculate that? Pi r squared is the area, so it's the other one. By the way, I think these are on the back of your formula sheet. Darian, you can check. The back of your formula sheet. Circumference is 2 pi r. And then we have a special symbol for the period. For once around, it is a time, but we use a capital T to kind of signify this is special. You only got one round. This is circular or centripetal speed. It's not on your formula sheet. But Riley, I've tried to show you that it's actually distance over time in disguise. And we can say that because we're going to be moving around a circle with no acceleration at a constant speed. Wait a minute, I thought you said we were accelerating towards the center. Actually, what the acceleration is doing is changing the direction, but not the speed. A concept closely related to period is frequency. We define frequency as the number of cycles per second. Period is the number of seconds per cycle. Frequency is the number of cycles per second. Period is the number of seconds per cycle. Frequency is the number of cycles per second. What that really means is this. Period is the reciprocal of the frequency, and frequency is the reciprocal of the period. If you know one, you know the other. If the period is 60 seconds, the frequency is 1/60th. Whatever the heck that is a decimal. And frequency is measured in hertz, symbol Hz. So this actually does also appear on your formula sheet. Does it say T equals 1 over F or F equals 1 over T? But I'm going to assume that also you can also use that to derive that f equals 1 over t, because it is technically 1 fraction equals 1 fraction, and stuff moves diagonally. T moves to the bottom, f moves to the top. Usually you'll know the period, but sometimes I may say find the frequency in hertz, or I may give you the frequency in hertz. Next page. So this gives us a weird situation. This gives us a very weird situation. An object is moving at 4 meters per second in uniform circular motion. It accelerates at 2 meters per second squared for 3 seconds. Jordan, what does A want me to find? Okay, don't write this down. This is wrong. A lot of kids go, oh. And then they don't write this down. This is wrong. Because we're at uniform circular motion, write this down. V final is 4.0 meters per second. Why? Because I said if you're moving in uniform circular motion, what can you tell me about your speed? It is what? Constant. But there's an acceleration, which is changing the direction, not the speed. How about the distance traveled? Again, don't write this down. Kids want to go, no, there's no accelerate. No. We're going to keep it simple. You want the distance? It's going to be, because we're traveling at a constant speed. You traveled 4 meters per second for 3 seconds, 12 meters. The other reason, Jake, that I can't use A, look at the vectors. These are not in the same direction. How dare you put one into the equation of the other? This goes back to all the way my Unit 1 rant about how dare you put a horizontal into a vertical or a vertical into a horizontal. There's a second equation for circular acceleration. In fact, I almost use the second one more. And I'll tell you why in a second. I already told you this. And I already told you this. I already told you AC equals V squared over R. And I already told you VC equals 2 pi R over the period. Jeff, I'm going to do this. How about I stick the 2 pi R over the period in for that V squared? This is going to give me a new equation for A. It's going to look like this. I'll get A equals bracket 2 pi R over T, all squared over R. But, Carl, I'm going to do a little algebra here, too. You okay with that so far? I'm just doing this. I'll call it I'm doing, for Physics 12, a simple substitution. Hopefully you've gotten much better at this kind of stuff and find, yeah, it's not so bad as it used to look. Kai, what's 2 squared? 4. So I'm going to write that as a 4. What's pi squared? I'm going to write that as pi squared. What's r squared? I'm going to write that as r squared over t squared. And Kai, what else is on the bottom outside of the squared? You know what? That's the same as having an r down there. Oh, how many r's on top? How many r's right now on top? How many r's right now on top? There's a squared, RR. How many on the bottom? You know what? One of these will cancel, and this gives us our second equation for acceleration. 4 pi squared R over T squared. Which one is correct? Depends what they give you. If you know the circular speed, use V squared over R. If you know how much time it took to go around once, use 4 pi squared R over T squared. This is the one when we go to Playland, and I just booked it as of about an hour and a half ago. We're going Tuesday, May the 12th. Usually, you know how you have a stopwatch, you know how long it took the ride to go around once. You have no idea how fast it's traveling. But to measure how long it takes to go around once, that's a simple start your stopwatch and wait till the same person comes by you again. Stop your stopwatch, you're good to go. So that's why I said I find in quote unquote real life, Josh, I use this one more. Okay. Both are on your formula sheet. In fact, I think your formula sheet says AC equals V squared over R equals 4 pi squared R over T squared. Use the one that matches the information that you have or has the variable that they ask you to find. So here's our summary. AC equals V squared over R equals 4 pi squared R over T squared. You don't have to memorize those, although you may get tired of looking them up, and a lot of my kids have them memorized during this unit and then let them fall back into their brain again. Where T equals what we call the period, how long to go around once. R is the radius. Oh, by the way, also, Sarah, notice I've ditched the vector notation. I know acceleration is a vector. What's the direction? Well, it depends where on the circle it is. I know it's always towards the circle, but that could be pointing northwards. I need a picture. So I'm giving you scalar equations, and we will use our knowledge of the diagram and physics to fill in any directional component that we need to. Oh, V, this is VC, and it's 2 pi R over the period. The circumference, distance, over time. So in uniform circular motion, where speed is constant, we have a strange situation. First situation, we're at a constant speed and accelerating. Why, Jeff? Because the direction is the part of the vector that's changing. So that is still a change in velocity. That means there is still an acceleration. And the acceleration vector is changing in direction because if you're right here, that's your acceleration. If you're right there, that's your acceleration. If you're right there, that's your acceleration. And Sarah, that goes back to my point of I'm ditching the vector notation. I'm finding magnitudes, and if they ask for a direction, I'm going to say, show me a picture. Okay. What that means, Riley, is we can't use this. That's a constant acceleration equation, and we have a changing acceleration. Direction is changing. I can't use D equals VIT plus a half AT squared. I can't use VF squared equals VI squared plus 2AD. I have to use the equation for uniform kinematics. I have to use my new acceleration equation, my new speed equation. I can still use D equals VT because A doesn't appear in there. Oh, and if I want a displacement, it's the average velocity over time. Can you take a look at your formula sheet? In this unit, probably more than any unit so far, you're going to be using the back page, the student reference part. So here we have gravitational constant when we get to gravity later on this unit. But in particular, we have mass of the Earth, radius of the Earth, period of rotation around for the Earth to go around once, period of rotation around the sun, radius of orbit around the sun, mass of the moon, orbit of the moon. Okay, so we have lots of information here. Why is that so important? Well, homework. You can certainly do number 1. See if I'm back. Number 1, nope, let's pause the video. I was doing so good. So number 1, find the frequency, 1 over the period. Find the speed, 2 pi r over the period, inwards acceleration. Number 2, for the moon. Number 3, for the Earth around the sun. 4 is good. Okay. By the way, 5, Riley, you and I are going to do. You ready? You've been in a car before?
I think so.
So if your car starts at rest and you jam on the gas, your body will seem to be pushed backwards. Which way are you actually accelerating?
Forwards.
Ah, so why does your body feel like it's being pushed backwards? I'm looking for a word that begins with the letter I. Your own inertia, your body, Newton's first, kicks in. It wants to stay not moving in a straight, it wants to stay at rest. And so what you're feeling is the car seat pushing you forwards, but you think, because all of us have our frame of reference very egocentric, we think the world and the universe does revolve around us, you think, oh, it's because my body's getting pushed backwards. It's the same phenomenon when you're moving in a circle. Have I beaten it out of you in love?
Yeah.
Good. Hang on, let me finish assigning the homework, Chief. 7 is good. Wait a minute, they gave me revolutions per minute. You have to convert that to revolutions per second, and that's the frequency, then get the period. Turn the page. 8 is good, 9 is good, 10 is not. Okay? We're now going to move on to part 2. I got some cool videos. We're going to do some free body diagrams. We're going to do lesson 2, and I'm going to get about halfway through it. Lesson 2, part 1. Horizontal circles. Hey, you know what? Next lesson we'll be looking at vertical circles. Starting out with horizontal circles. Right. It's not here. Never should have let him go. Jeff, imagine that you're in a car turning a corner. What direction is your acceleration? That's the first question. And what direction is the force that acts upon you? What direction is the acceleration? Now, hopefully, you've seen enough of these chart questions on your tests that you've clued in. You go like this, you go like, and you cross out C and D. Go down one column at a time. I never try and look at all my answers. Ron's going to put his phone away before I take it away. Thank you. What about the net force? I'm going to give you a hint. F equals what? Go very basic, back from Physics 11. F equals Newton's second law. MA. Force is a vector. Is mass a vector? Is acceleration? So here's my question. Hey, where do you think the force vector gets its direction from? The mass or the acceleration? So what can you tell me about the force direction and the acceleration direction? They are the same. So can you, net force, inwards or outwards? What's the correct answer, Jeff? It says explain your answer using relevant principles of physics. We just did. Okay. Force gets its direction from the acceleration vector. In fact, not only is F equal ma, turns out circular force is equal to ma circular. That's going to work. Now, we have two different equations for A now, v squared over r and 4 pi squared r over t squared. So we'll have to modify that part of things a little bit, but it's still going to be ma. In fact, instead of circular force, we have a special word. In Latin, the word centripetal means towards the center or center seeking. So when an object is moving in circular motion, it has inwards centripetal acceleration. So I'm going to use a subscripted C, and you can pretend that the C stands for circular. Really, it stands for centripetal, but circular is an easy, dumb way, Carl, to remember that you're moving in a centripetal acceleration. By Newton's second law, actually, by Newton's first law, if you have an acceleration, there must be an unbalanced force if you're accelerating. So the object moving in a circle has an inwards or centripetal net force. Some like to use in fact, I like to use the following notation. If I see this, I usually assume you're talking about unit 2, winner minus loser, everything in a straight line, or if something's at an angle, parallel, perpendicular. If I see this, I assume we're moving in a circle. I won't take marks off if you're moving in a circle and you don't put the C's, Darian, but to me this is an easy way for me to keep them straight. Okay. What that also means is F equals mv squared over r, or Fc equals m4 pi squared r over t squared. You want the most common dumb mistake in this unit, Kylie? Because these acceleration equations are so complicated, I see that all the time. Kids forget the M. They're so proud. I got the acceleration. Yeah, you're telling me force equals acceleration, which is nonsense. Oh, and often that means that masses that were supposed to cancel now don't cancel. And you're going to be getting all sorts of haywire answers. So I rarely jump straight to this. I usually go MA, drop the M, and then fill in the acceleration component. That's the first key idea. The second key, Sarah, what did I underline here? Those two words, the last two words. Nice and loud. Darian's going to stop moving his paper. Net force. So here's what the second thing, this is important. In our winner minus loser approach, the centripetal force will always be the net force. And what that means, it will never, ever, 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 ever actually appear on your free body diagram. You will never see an FC. The same way you never saw an F net. When we went winner minus loser, Jeff, what we were really saying is we're going to do all the subcomponent forces equals the F net appeared in my equation, but not on my free body diagram. It was the vector sum of everything. FC will never appear on your vector diagram, on your free body diagram. Carl, it will appear in your winner minus equals FC. How will I know it's FC? Because you're moving in a circle. If you're not moving in a circle, it's MA. If you are moving in a circle, it's MAC, which is going to be MV squared over R or M4 pi squared R over T squared. Let's do an example. Let's drive a car. So questions that you can handle. Stuff we can already solve. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what is the maximum speed that the car can safely travel through one turn? Most of you are driving now. You may notice when you're coming to a sharp corner, there's a speed sign that tells you to slow down. Here's how they calculate it. Okay. Now, this isn't exactly how they calculate it. In real life, they would probably take the answer that we get and divide it by 2, assuming you're stupid. Or they would have to take into account bad weather coefficient of friction. I've given you the coefficient of friction, but this could be when it's dry, and we don't want when it's raining for you to have to go flying off into the woods. But it starts like this. What do they want me to find? What path are we tracing out? Don't overcomplicate this. A circle. This is a job for a free body diagram. I'm going to do 2. I'm going to do and I'm going to do both of these have their uses. Top view. So let's say here's the corner the car is going around. Here's the car traveling that way. But I don't want to put that on there because that looks like a force. How can I show that the car is traveling that way? Usually somewhere in the center, I do that. And if it's on the radius and archy, I say, oh, that's the path. What are the forces acting on that car? Get the obvious one. Which way is gravity if this is a top view? Yes, okay, how do I draw into the page? I really can't. Is this car sinking into the ground like quicksand? Is it flying into the air like Superman? So there must be a force coming out of the page. Which force? Normal. They're the same size. I don't know how to put it on this diagram, so on the top view, I'm going to leave it off for a second. What path is this car tracing out? Don't overcomplicate. What path is this car tracing out? Where must the net force be pointing? There has to be a force that way. That's not FC. But here's my question. What force is that? What? Acceleration is not a force. Thank you for playing. What force? Inertia is not a force. Inertia is mass. Thank you for playing. Let me get my question out. What force pushes a car in a circle? Why can't you turn on ice? Friction. If I do a front view, here's how you draw a front view. You do 2 rectangles for the tires, a big rectangle for the front, you add the headlights and put a trapezoid, and that looks like a car coming towards me. It's meant to be a stick figure diagram, but Cole, it works. Now I need to show you whether this car is turning left or turning right. Here, I go like that. I put a little axis and a little archy, and that's saying it's coming out of the page towards me, and it's going to go whizzing over my left ear and coming around. Okay? In some ways, the front view diagram is more descriptive because what are the forces acting on this car? Get the obvious ones. Which way would gravity be in this picture? Straight, see, and now I can fit it in. What else? What path is this car tracing out? A circle. Where must there be a net force pointing? Toward the... I'm not going to call that FC. Oh, what force pushes a car in a circle? So I did the top view picture. I usually go with the front view picture. I find it more descriptive, and I have to be honest, as someone who sucks at art, the fact that I can draw a half-decent stick figure car makes my little math nerd heart go, hey, at least it's legible and recognizable. Okay. Vertically, who's winning? Trick question. No one. So centripetally, I didn't say horizontally. Centripetally, who's winning? What's the only force pushing you in a circle? Winner, no loser, equals FC. Where FC equals MAC. MAC. Friction is what times what? Alon. I had 3 people murmur, Alon. Friction is what times what? Now, in this case, look. What is the same size as the normal force in this particular diagram? So I would live with it now if you went in now, if you had said, if I said to you, friction is what times what, and you said, well, in this case, it's mu mg, I'd live with that too, because you would have done 2 steps at once. But we'll put it in our notes. Equals m. Which equation do I want to use for A? What do they ask me to find? I guess I want the one that has a v in it. V squared over r. Hey, what do you notice in this equation? Turns out semi-trucks can go on the same roads as motorcycles, which you knew, but that's why. Turns out the speed will, they don't have to have separate speeds for motorcycles and for cars and for trucks and for SUVs and for semis. One speed fits all. What are we trying to find? V. How would I get it by itself? V equals mu gur square root. I'm betting if you're a road engineer, you have that formula memorized. However, I'm betting the mu that you use is the rainy or maybe even icy weather mu for safety. Okay? But this is where those road speeds. And you know what? I'm also betting you probably divide it by, you knock off an extra 30% for safety to be paranoid. This is going to be, what's mu? I don't know, what's mu with you? I think at 0.45, is that what I said? 0.45, 9.8, and what did I say the radius of this corner was? 60 meters. What's the maximum speed that I can take this corner at? .3 meters per second. Now, I made these numbers up, and they're not great. If you go times by 3.6, it's saying you can do this at 60 clicks. Okay. Well, I got to be honest, Jake, this is the, if you exactly did that speed, you would feel very uncomfortable because you would feel through your steering wheel that your tires were really, really wanting, I won't say to slip off, to keep going in a straight line at a steady speed while the road curved away. You would feel very uncomfortable. You would feel, because you've all seen, I'm assuming all of you at least once have driven on snow or something where you felt through the steering wheel, uh-oh, I'm right on the threshold of yuckiness, I better slow down. You would feel it. So probably, what would they post? You know what? Probably 40 clicks. 40 clicks. Example 2. Example 2. A test tube wrote, oh, by the way, Ben, I like example 1, I like example 1, I like example 1. Good chance something like this. It's a nice application. It's a good use of circular and centripetal forces. A test tube rotates with a period of 9.9 times 10 to negative 4 seconds. What is the centripetal force on an amoeba at the bottom of the test tube, So we call these things centrifuges. By the way, centrifuge comes from the mythical centrifugal force, which is not a force at all. They really should be called centrifuges or pedal, I don't know. Anyways, no big deal. What's this question asking you to find? Speed? No. Period? No. What's this question asking you to find? You know what? Since it's asking me to find force, I might go straight to saying maybe F equals MA. Oh, FC equals MAC. Maybe I can just plug and chug, which is going to be M. Which equation do I want to use for acceleration? The one with period in it. How do I know? That's what they gave me. So I'm going to use, Anthony, the 4 pi squared r over t squared. Let's double check. Do I have everything? Did they tell me, Anthony, the mass? Yep. 4, I know. Pi, I know. Did they tell me the radius? Right there. Did they tell me the period? Oh, okay. All of you, every one of you, you want to figure out how to type this into your calculator because some of you might get some funky errors. It's going to be, what's the mass? 1.8 times 10 to the negative 9. 4 pi squared, what's r? 0.15 divided by 9.9 times 10 to the negative 4th. You want to learn. For example, some of your calculators might not let you go pi squared. You might have to go pi times pi. I don't know. Try this, please, on your particular calculator. I'll show you what the answer is, and then I'll come help any of you that can't get that. (1.8 negative 9 4 pi squared r over t squared). You should get that 0.019. Sorry, 0.0109. And it's a force. What would my units be? Yeah, still newtons. See if you can get that. If you can't, raise your hand and I'll come help. This also, by the way, is one of those units where I see time and time again kids write all the right numbers and just can't get the right answer. This unit will have the longest question of the year in terms of number of lines of writing and the amount of typing. Okay? So longer than the collisions at angles from last unit by about 3 lines. Not as tough. It's much more plug and chug, but it's plug and chug on steroids. Big time. Okay? Let me pause the recording. By the way, this force may seem really small, but if F equals ma, if you divide this by the mass, which was 1.8 times 10 to negative 9, the acceleration in meters per second squared is that. Or if I divide that by 9.8, it's experiencing 616,000 Gs. This, what the centrifuge basically does is it rips apart the amoeba into its constituent parts. It shreds it, and that's one of the ways that they use centrifuges in labs. And it turns out because it's angled, the various masses, the lighter ones will climb higher, the lower ones will stay lower, and you can separate the components. Don't need to know that, but nerd trivia. Next page. Example 3. An empty swing on an amusement park ride, check, has a mass of 10 kilograms. If the swing is a kinetic energy of that, what's the centripetal force on the swing? Well, they want me to find centripetal force. Centripetal force, F equals ma. C. Which A am I going to use? Am I going to use, or am I going to use, did they give me the V? Did they give me the speed or the period in the question? No. What else did they give me in the question? Okay, well, I know that kinetic energy equals what? As an equation. Half mv squared. Oh. You know what? Maybe I can find V here, and you know what? I think I'm going to use that one. I think it's going to be Fc equals mv squared over r. In fact, before we plug and chug in numbers, let's get the v squared by itself in this equation. How would I get the v squared by itself in this equation here? What would I do with the m? Divide. What would I do with the 2? Times. Do I care about the 1? So you know what? An expression for v squared is also 2 times the kinetic energy divided by the mass. Why don't I plug that in here? Here's a new equation, not on my formula sheet. I'm not going to write it down. I can derive it. Equals m over r, and then I have 2ke over m. Wait a minute, Mr. Dueck, don't you need to square that? No. I substituted v squared for v squared, right? So I don't need to add an extra squared. Anything you notice here? Have any of you been on the wave swing like this at Plateland? Yeah. Next time you're on it, look at the empty chairs. They don't swing higher than you. They don't swing lower than you. They swing at the same angle as you. Why? Mass cancels. Now, that's not going to be quite right. When you're in the chair, you have a little bit more air resistance than an empty chair, so you might be a few degrees lower than the chair, but it's pretty much bang on. You certainly won't see the chairs like way up here while you're hanging down here. Oh, let's crunch the numbers. Fc then is going to be 2 times 460 divided by 7. It's going to be 2 times 460 divided by 7. The centripetal force, 131 newtons. 131 newtons. Next page. I like example 4, I like example 4, I like example 4. Almost certainly. A car can travel without slipping at a maximum speed of 32 meters per second in a circular path of radius 72 on a dry horizontal surface. Now, we need to change this question. And the reason we need to change this question is I've made up bad numbers. So where the radius is 72, put a 1 in front of it. Let's make the radius 172. I'm hoping that'll give me less bad numbers. They're still going to be bad, but they're not going to be nonsense. When it rains, the coefficient of friction is reduced to 1/2 its original value. What's the maximum safe speed of the car under this wet condition? So it seems to me, in this question, I have 2 parts. 1 part when it's dry, 1 part when it rains. I'm going to do a free body diagram, front view, but I already know from prior experience that I need lots of room. So I'm going to do the free body diagram above the question. I'm going to say, okay, here's the car. And you know what? Just for giggles, I'll have it go around the corner this way. Now it's making a left turn instead of a right turn. What are the forces acting on this car? Get the obvious ones. Is the car sinking into the ground like quicksand? Is it flying into the air like Superman? What else? Let's get the normal force. What else, Jordan? That's what's pushing it in a circle. Friction. What's my equation? Let's go to the rainy side because it wants us to find the maximum safe speed under this wet, rainy condition. I suspect we'll get partway through, come to a halt because we're missing a piece of information, and maybe be able to figure it out from the dry side. But let's start the rainy side. Vertically, who's winning? No one. Horizontally, who's winning? Now, it doesn't equal MA. What path am I tracing out? It equals FC, which is going to be MAC. Alon, in this case, friction equals what times what? Although they gave me the mass of the car, apparently so far they didn't need to. Maybe it doesn't cancel out later on. I don't know. Which version do I want to use for acceleration? What are they asking me to find? Speed? Let's use the one that has speed in it then. And again, you'll notice, Josh, I'm picking my words very, very... No, it was Trev. I was right the first time. I'm picking my words carefully. I'm saying speed because if I had said velocity, there's a direction. Oh, it's going around a circle. I don't know what the direction, but speed, I'm getting the magnitude. It's going to be mu g equals v squared over r. Oh, you know what? We get the same thing we had before. V is going to be mu grr square root. Do I know R? 120. Sorry, 172. 172. What don't I know? What's mu with you? Oh, let's walk to the dry part. Maybe there's enough there. When it's dry, you know what? Friction is still what's pushing me in a circle. When it's dry, it's still mu mg equals m AC. Ha! Mass cancels here too. Oh, yeah, because a truck and a motorcycle and a semi and a car all drive on the same road. This is going to be mu g equals v squared. How did you know to use v squared over r? Because they gave me the speed when it's dry. By the way, the other reason this is a bad question, what is the maximum safe speed when it's dry? Yeah, I'm letting you go 115 kilometers an hour around this corner. That's like freeway speed, not having this. Okay, so. Well, the problem, honestly, Miller, at this speed with the 72, the coefficient of friction ended up being way bigger than 1. You had to have like professional dragster tires. And no, you couldn't do Tokyo drift because that's now you're sliding. Friction is no longer maximing out. So that wouldn't apply to this question. Mu is going to be v squared over gr. 32 over 32 squared over 9.8 times 172. Oh, I hope I get a better mu here. .6, whew, that's better. 0.6075. What are the units from you? Okay, no units. Now, it says when it rains, coefficient of friction is reduced to 1/2 its original value. So I'm going to go divide by 2. I guess when it rains, the coefficient of friction is 0.30375. The maximum safe speed is going to be 0.30375 times 9.8 times 172 square root. .6 meters per second. Okay. Technical comment on turning. The reason that friction is inwards really has to do with how wheels work. So if you look at my picture here, when you turn the wheels, your car wants to keep going in a straight line at a steady speed. So the wheel tread applies the force in that direction if you add up the vectors. And forces come in pairs. The road then applies the force in this direction towards the center, and that's what turns the car. Oh, and if the wheels apply a bigger force than the road is capable of exerting, now you'll have an unbalanced force. You're going to continue to accelerate forwards. And you'll feel like you slid off the circle. Actually, you kept going in a straight line at a steady speed, but the road curved away from you. Let's go into outer space. We'll finish up with this. One method of generating artificial gravity in outer space. Let's see how many more to 1, 2, 3. Yeah, I got to get this one done. One way to generate artificial gravity in outer space would be to build a circular space station, something like this picture, and then spin it. So, there's a picture, stick figure picture. If this space station has a radius of, this is also a yucky question, cross out the 5.2. Let's make this a big futuristic space station. Let's give it a radius of, oh heck, 120 meters, which means its diameter, it's 240 meters across. Let's go maybe 100 years in the future. Let's go something like this, okay? What does the period of rotation need to be for an astronaut to experience 80% of the Earth's gravitational field? I like this question, I like this question, I like this question. Not just that, it's space. This is our best guess, Jacob, if we do like a Mars mission or something even further, and we don't want the astronauts' bones to decay and atrophy, spin the space station, and you can induce an artificial gravity. So, let's do, you know what? A free body diagram. Actually, let's label the forces. Let's do the diagram, the top view. What are the forces acting on this person? Get the, oh, wait a minute. Why can't I get the obvious one? Okay, we're in space. What else? What path is this person tracing out? Where must there be a net unbalanced force pointing then? So I know there is a force that way. Question is, what force? Don't say FC. FC never appears on my free body diagram. What's pushing this person in a circle? What are you? You were closer than you realize. What? The space station's floor, which we can call a normal force. So in this case, normal force equals Fc. I don't know the normal force. And I can't say, look, oh, wait a minute. They told me how big I want the normal force to be. They told me I want the normal force to be 80% of gravity. There. So I'm going to get this. 0.8 mg equals MAC. Oh, what do you notice? So this space station, if you were a little toddler, you would feel 80% of your own weight. Or if you were a full grown-up, you would feel 80% of your own weight. Doesn't matter what your mass is. That's kind of handy. Which version of A do I want to use? Go read the question and see if you can figure it out. Period. Oh, they mentioned or asked for the period, then I better use the one that has period in it. So it's going to be 4 pi squared r over t squared. If you wanted to build this space station 120 meters of radius, 240 meters all the way across, and you wanted to have an artificial gravity of 80%, you'd have to have it spinning every how many seconds? How would I get the t by itself? Well, you know what? I think this is 1 fraction equals 1 fraction. I think I can use my stuff moves diagonally. I think you'll get this. T squared equals 4 pi squared r over 0.8 g. Yeah? Oh, and how do I get rid of a squared? The period of rotation for this space station is going to be the square root of 4 pi squared. What did I say r was? 120? Yep. Divided by 80% of 9.8. This space station would have to rotate every how many seconds? Oh yeah, I'd practice this one too. I get every 24.6 seconds, which is still in real life a bit fast, but getting more realistic. Anthony, what if the radius got smaller? Would this space station have to rotate faster or slower? Faster. Bigger space station, you don't have to spin it as fast. What if we didn't want as big a gravitational field? Don't have to spin it as fast. What if we want more gravitational field? Spin it faster. Your homework right now is to finish the stuff from lesson 1. Tomorrow we'll pick up with lesson 2. Got a couple of cool videos to show.